Okay, hello everyone, and welcome to today's Lunch and Learn session. This is the first of a four-part series that we're doing in collaboration with the University of Essex. I'm joined by Mays Al Naday. We'll be introducing ourselves properly in a second. And this Lunch and Learn series is really about taking some time just to go through some of the kind of key topics, I suppose, in what's happening in digital technology right now. So you'll hear terms like digital twin and AI and ontologies, perhaps, and you may be sitting there and thinking, what on earth does any of this mean? And so we felt it would be a good idea just to put together these hour-long sessions that anyone can come and participate in. And kind of cover some of these topics. So this first session is titled Demystifying Digital Twins. It's a meaty topic. It grounds pretty much all of the preceding sessions. And the agenda that we're going to follow, if I can navigate my screen, is as follows. So we'll start with some very quick introductions. And then we'll go through the topics in this order. So we'll start by talking about why digital twins became so confusing. Because digital twins mean many different things to many different people. So we'll sort of cover off why that is. Then Mays is going to take you through a simple definition, the spectrum of digital twins. It's not a binary topic. There's lots of different variations of it, and the building blocks of how to build a digital twin, how to get there. And then we'll both sort of jointly discuss where the field may be heading. So what does the future look like? And we'll finish off with an example use case, really to sort of bring all of this together. A couple of housekeeping points. There is a chat function enabled. We have it on our screen. So the way we're going to run the Q&A is interactive. So it's going to be through session. So if you have a question on a particular point, drop it in the chat. We will do our best to answer that as we go. Any questions that we don't answer, we'll try and wrap up at the end. So yeah, feel free if there's anything that we say that you think, oh, don't quite understand that, or I'd like you to go further on that particular point, please drop a note into the chat. Second thing is that this webinar is being recorded, so we will be sending the recording link out to everyone that's registered for the event post-session. And then probably afterwards it will be available on something like YouTube or whatever, but that will be directed by our social media channels. And the third housekeeping point is more really a kind of cautionary note. This is a high level webinar, so we're not going to go too deep into any of the topics. We're going to try and go through those that meaty agenda and cover a lot of ground. If anyone wants to go deeper into this on a sort of one-to-one basis, I'm sure Mays and certainly myself would be more than happy to have those discussions. So without further ado, introductions. I'll go first. So I'm Toby. I'm Toby. I'm the founder and CEO at a company called Entopy. We're an AI and digital twin company. And we have been working in close partnership with the University of Essex now for probably the best part of 4 or 5 years, I'd say. And Mays has been a big part of that. So I'll pass over to you, Mays, if you wouldn't mind just giving a quick introduction.
Absolutely. Thank you, Toby. So my name is Mays Al Naday, and I'm a senior lecturer at the University of Essex. I specialize in cloud services, the resource management and orchestration, and cybersecurity, and digital twin being one big part of such services. And we've been happily and actively working with Entopy on a range of research and innovation collaborations to make digital twins even more efficient. Yeah, back to you, Toby. Thank you.
Brill. Thanks, Mays.
Glad
So
to be with everyone.
there you go. That's what I wanted. I wanted you to say that. So yeah, no, I really do appreciate you being here, Mays. And for everyone that's watching, it's very rare that we manage to get some of Mays's time because she is unbelievably busy. So let's kind of make some progress. So let's start off with why digital twins became so confusing. And I've put together a bit of a timeline to try and articulate this. I suppose the point is, why is everything described as a digital twin? Okay, and this is speaking from the perspective of being a digital twin company. So there are often I'm often in rooms where there are arguments around what the definition of a digital twin is. Frankly, my position on this is it doesn't actually matter. Um, but um, but it's worth covering off why the definition has become so wrangled. So digital twin, or the concept of digital twin, started way back in the 70s. The first reported use of, whether they used the term, I'm not sure, but certainly the concept was on the NASA Apollo 13 missions. So when everything was going wrong, they created a simulation on Earth that they could test certain things. If you've ever watched the film, you can kind of imagine they're sort of testing different scenarios and so on and so forth, and seeing what works, right? So that was the origin. It was very much a physical asset. It was a mirrored model. And then as we went into the noughties, this concept of modeling life cycles started to appear and started to gain some traction, but it was marginal, really. The concept of digital twin hadn't really caught sort of mainstream. It certainly wasn't a term being used by marketers. Then in 2010, probably a little bit later to be honest, but 2010 was the first signs of IoT, but this really exploded. And if anyone's ever tracked any of the metrics with regards to how many devices have been connected and so on, it really is quite a dramatic growth curve. But what this meant was all of a sudden the physical world was being connected to the digital through sensors. So sensors were there recording where they were, location wise, temperatures, vibrations, all sorts of things. And this explosion of IoT has created loads of data of the physical world, which of course can be modeled or built into a digital twin. So when you're looking at how do we describe what we're doing here with IoT, many people started gravitating towards the label of digital twin. Clouds and dashboards accelerated that. They made the physical, the sort of digital models or digital representations very visual, very cool. It started to look a little bit more like Tron, or the sort of thing that you would expect a digital twin to look like. And then as we saw the emergence of AI and predictive models, and of course AI models have been around for a very, very long time, but as we started to try and apply them to real world environments, again, we needed a way of modeling and mapping where those AI predictions fitted, I suppose, in these computational models, and how they all link together. And digital twin is a natural way of describing what's going on there. We saw the explosion of the metaverse. So I've put hype in there quite intentionally, but the metaverse sort of idea of being able to live in a digital environment and interact with that environment, and sort of extensions of games to kind of become a partial reality. And so much was it an explosion that one of the very big famous companies changed its name. And then we're now into the world of, we've got these wonderful things called large language models, and we need to figure out how we can take them out of computer screens and start applying them again to real world physical environments. And digital twin is playing an important role there. So what you can see, hopefully, is as we've gone through that curve, the label digital twin has evolved. It's been manipulated, it's been shifted and changed to a point where the actual term digital twin becomes quite confusing. And I think that's a good opening for the next slide, which is a simple definition. So over to you, Mays.
Sorry, I'm muted. Yes, thank you very much, Toby. That was a really good capture of history. So what is a digital twin? If you think where we started, is a process or a system that has some physical assets, and it applies some logic, and it draws some consequences based on that. So a digital twin basically is a digital representation. It's a virtual representation of that real world entity. Um, that could be a process, that could be that system. And this is basically connected together. The different components are connected together. Um, and we use that digital twin so that we can evolve our understanding. We can analyze it. We can apply different what if scenarios on it. We test different decision making strategies and see how that behavior change. Think of it this way, is a good example is if you take a car, if you take a normal car, if you take the real car and you try to play around with it and change it and apply different gearing mechanisms, different braking mechanisms, yes, you will draw some intelligence, but ultimately you will result in destroying the car. So we realize that this is quite a costly way of optimizing a car before we actually come with a new version. So as time went by, we started creating these digital simulations of the different components in the car, and we connect them together. So ultimately, we end up with a piece of software which looks like the car, but it's only hypothetical. That piece of software that looks like a virtual car is what we call a digital twin. And a car is one example. You can take a university, and if you can create virtual components of the university and connect them and make decisions and data flow from one department to the other, you will end up with a digital twin of the university. You can then apply these analysis on how it behaves, how decisions flow, how data flow from one to the other. You can test different decision-making strategies and you can optimize them over time. And when you reach to a state where you think, yes, this is a good outcome, it achieves what I want to do, you can then take that and apply it to real systems. And as time went by, we found this way to be far more efficient and far more cost effective compared to testing on real things. Hence, digital twins now are proliferating in the world. So, hopefully that's a simple definition. What's a digital twin? It's not a spectrum, it's not a binary process. It's not a binary entity. Creating a digital twin involves a spectrum of operations and stages to end up where you want, which is basically the cognitive analytics and insights that allows you to optimize your operations. You start normally by some static model, and this could be mathematical. It could be taking a snapshot of your data, what we call an offline data, and you analyze it. That gives you a checkpoint in time about how your system behaves, either based on assumptions or based on the temporal state or the state of the system at that point in time. That is good. That's where you need to start. But then that system could change over time. Or if you take that system and you apply it somewhere else, in a different space, that could behave differently. Take, for example, the car. If you drive in Colchester, where we are, it could be different than if you drive in London or in a Newmarket, simply because the roads are different. So what you need to do is then you need to monitor the assets that are involved in the system for which you want to create a digital twin. The objective is that then you collect data that indicate to you the status of that system and the behavior of it at different points in time and in different places. The next thing you need, what you will end up with in here is volumes of data that could be different, but they have semantics. Semantics is basically what is the meaning of the data, what is the context of that data. And different data could have correlated and connected semantics. So, for example, the gear of a car is directly correlated to the engine of the car, and the semantics of data you draw from the two are linked to each other. So, what you need to do is you need to connect in a logical, in a meaningful fashion, these different assets so that you can create what we call ontologies, which are connected representations of the data. So you integrate them together to create a map that tells you if you do this, if your brake is behaving in this way at this point in time, and at that same point in time, your engine is behaving in this way. So then you take them and you put them into simulation models, and these simulation models will say, in simulation models, you need assumptions. So it will say, you have these connected representations. If you apply these assumptions, this is what the behavior meant. And this is what will happen if the data change in a certain way. So then you can take that and you create an operational digital twin out of it, which then you can say, well, what if I change this? What if the data changed this way? From that what if scenario, you can then draw intelligence about how the system behavior will change, how much will it cost you, how much will it gain you, and based on that, you tweak and change your decisions to come up alternatively with the most optimized outcomes based on your business intents. That's in overall gives you a mature digital twin. So then if we move next, what are the building blocks? First and foremost, you need data. You need data from your system in order to capture the status of the system. Sure, I can go and draw mathematical model, but even in my mathematical model, either I'm going to feed realistic data or I am going to make assumptions about the system behavior and from that to draw data. If I do the latter, yes, useful, but I could be making so many assumptions that render the model inefficient, and I still need some real data to capture the reality of the situation. Then what I need to do is I need to integrate this data using its semantics. I need to know that this data from my gears are related to this data from my engine, and I need to bring them together so that I can create a coherent vision of my assets. I then need to introduce them into something that analyzes this data and says, right, okay, you have this increase in your gear, your engine consumption of petrol because you did this in your gear. Okay. So it analyzed the engine data and analyzed the gear data. Normally, I mean, we started historically by some mathematical models that looks at the data, draws something about the average and the standard deviation. Nowadays, we moved into machine learning models. This was about something like 7 years ago, models that looks at tabular data. And nowadays, we are looking at LLMs and generative AI to actually look at different data modalities. Now, all of this is good, but it's worthless if I try to bring a command line terminal and run a model and show you the output on a terminal because yeah, what does that mean to anyone? I might, like some researcher hidden in a lab might be able to understand it. Very few niche amount of people might understand it, but it doesn't give you a big picture. So none of it is worthwhile until you start visualizing it and see the curves going up, going down, see the red alerts and the green alerts, so that you know how is this behavior have been affecting your system. Now, by the time you get to all of that, by the time you collected data, processed them, drew intelligence, and visualized it, to be able to do all of this, you are ending up with the digital twin itself being a system that you need to manage. And you need to be able to run it and manage it in an efficient way so that you are able to then draw data and do all of this circle in an efficient manner so that not only your operations are optimized, but your digital twin is also optimized. So then if we move to the next stage, right, optimizing applications is, well, optimizing digital twins by itself is a process because to be able to run them, you need an underlying infrastructure. So in here, we mention a couple of efforts where we are looking at optimizing the underlying infrastructure that runs digital twins. This, particularly the network project, is an EU smart network and services project where we're looking at developing cybersecurity and resiliency functions for 6G ecosystems that are expected to operate digital twins. And the idea in here is that we provide reliable, trustworthy infrastructure underneath so that we are able to manage and run digital twins in a sustainable fashion. And this in here is a project where there are a number of outcomes and proofs of concepts. One is about cloud orchestration. The other is about cyber threat intelligence. And observability of cybersecurity postures, which are we are in continued collaboration with Entopy to see potential exploitation where we can transfer knowledge in here that could be useful for digital twin operations. The other project this is a European, this other one project, this is a national Innovate UK project. It's a knowledge transfer. And this is a direct collaboration with Entopy where we are looking at how can we create reliable digital twins for operational environments that do not generate sufficient amounts of data. And how can we take different AI models that are applied for different digital twin use cases, generalize them and reuse them for multiple use cases. And the objective, again, is to make digital twins sustainable in their operation in the longer run, because I don't want to keep developing models for each use case. I want to be able to bring the knowledge that, well, Entopy want to be able to bring the knowledge that they gain from one model and adopt it,
Hmm.
and adopt the insights, adopt the model operations into a new use case. And we don't have to go through the same cycle again. Also, if I have one use case which does not generate sufficient amount of data, remember in that cycle we went through, the essence, the starting point is having data assets. Well, what if I don't have enough data assets? What do I do? Shall I pack and go home? No, I can't do that. So in this project, we're looking at innovative ways of actually generating amounts of data that allows reliable digital twins. Moving from these efforts, then we're looking at what will be the shape of digital twins and future systems with digital twins. This is actually more about the complexity of digital twins. So I hand back over to you, Toby.
Thanks, Mays. And I thought that was I said it was going to be light. I don't think that was light. I hope everyone found that really interesting. And I will just remind people, if you have questions about anything that has just been said or is about to be said, drop them into the chat. We're keen to make this as interactive as possible. So what Mays has just described is how complicated these twins are, these digital twins are, and how many different aspects to them there are. And there's a group in America, there's a group in the United States called the Digital Twin Consortium. I actually think they're global. There's obviously the Digital Twin Hub in the UK, which is an amazing and fantastic sort of entity in the UK, which is really driving the message. But other consortia, other think tanks, and so on are producing things that try essentially to structure everything that's going on. And like I said, the Digital Twin Consortium have actually produced a periodic table, which in itself explains how many different aspects or technologies are involved in creating digital twins. But it's worth bringing up because in really simplistic terms, you have lots of different technologies that ultimately unify to build a digital representation or twin or model. And as Mays has said, there's lots of different stages of that. The UK definition is that there are digital shadows, moving all the way through to fully fledged digital twins that just recognizes the complexity, the fidelity, and the I suppose integration of digital twins with the physical counterpart. But what this periodic table helps to illustrate is the various technologies that are involved in doing that. So it's nicely put together because it buckets it into 6 key areas. First of all, we have data. So what technologies are there around data? Okay, so you have data streaming technologies, batch processing technologies, real-time processing technologies, all of these sorts of things that sit within the digital twin periodic table that recognize that data needs to be served and services need to provide data to hydrate digital twins, for lack of a better phrase. We need to integrate them. So everything in yellow are technologies that are key to integrating data into digital models. And once we've got that integrated data, we can then start to derive intelligence. And that's where the purple tiles start to play a world. Now, what's important to say here is there are many ways to skin a cat. Okay, so you might want a digital twin to predict certain things and orchestrate data as opposed to simulate. When you get into the world of simulation, there's lots of different ways to simulate different things. I always use the phrase, if all you have is a hammer, everything looks like a nail. So be very, very aware when you're exploring digital twins in your own contexts, to understand, the profession and the vantage point of the group that you're speaking to. But there are lots of different ways, and the whole point here is that it's collaborative. So lots of different technologies work together to deliver comprehensive and holistic intelligence. Then we need to visualize it. So this is where the UX comes in. So the sort of pale green that you've got. And there's lots of different technologies that are going on in the visualization stage. The most common, of course, is dashboards. But then you get into the world of XR, extended reality. So you can start interacting with these digital twins with goggles. You've got gamification, which is a really neat way to try and drive engagement. That's the best way I've seen it. But again, you've got lots and lots of different ways of doing this. You have management. So Mays just touched on some of the projects, and hopefully you understand the depth of those projects that are talking about very, very, very specific components within this. And of course, you have trustworthiness, and this is something that I think we have a session that specifically talks about security and secure by design principles. But there's a lot of work going on here as well to ensure that these digital twin models are robust, they're secure, they're reliable, they're trustworthy. So all the way through, there are lots of different technologies that you may recognize as distinct components, that you may recognize as technologies that you interact with in their own right. But this periodic table sort of groups them together and illustrates just how many technologies the phrase digital twin umbrellas. Um, so if I just move on to the next slide, one of the big advantages with digital twins is if we think about an enterprise, if we think about an organization, there's going to be lots of different stakeholders within that organization that are having to make lots of different types of decisions. And those decisions are going to vary by frequency, so how often you make them and how many decisions in that category, if we bucket them, you have to make, and time horizon. So if I'm making a decision, how far in the future am I making that decision about? How far in the future is the event I'm making the decision about, right? And we've done a little bit of work to try and visualize this. This isn't, comprehensive. It's designed as a slide. But we've got four types of decision-making horizon. So you have real-time decisions. So this is, I'm in the car, I'm driving, what do I do now? That's a sat nav, right? So think about it in terms of the sorts of technologies that you might interact with. But real-time decision making is, I need to know what the next 2, 3, 4, 5 hours look like. I need to know what's happening right now. I need that kind of holistic picture. Tactical is, what route am I going to take next week? Okay. When do I need to get my car serviced? These are kind of tactical decisions, and you're going to be informed by lots of different things to help play it. I hope you can acknowledge, Mays, I'm following your car analogy through here. Um, Strategic, when do I need to, I don't know, upgrade my car, right? So, when do I want to change my car? When do I want to sell it? What does that look like? And then when we get to transformational, we're talking about, I don't need a car anymore, I need a plane, right? Or maybe I don't need to own a car, maybe I can share a car, right? So it's fundamentally changing the way you interact with it. So what I've just done is illustrated decision-making horizons using the car analogy. If you're in an enterprise, real-time or day-to-day operations, what's happening on the coalface? How do I manage this particular challenge that's in front of me? Tactical would be more around staff planning, resource planning, that sort of thing. Strategic would be, where do I spend this money? Which partner do I choose? How do I work? Transformational would be, which direction do I take the business in? Right? Now, there's lots of different stakeholders that are making those decisions. And one of the real advantages that we're seeing with Digital Twin is that you have these models that have all of those capabilities built into them, and they create this kind of unified intelligence picture. This is a phrase that we're starting to use at Entopy, and we're seeing starting to actually gravitate within the industry. And the idea is really simple. All of these decision makers need to make decisions, and they're making them in very, very different context. And it would be great if all of those decisions were being made from the same source truth data or the same source truth model. That would be that's the absolute utopia, right? At the moment, these decisions are made in isolation using lots of different tools. So you end up with disconnects between strategic decision makers and operations guys on the front line. So one of the real advantages with digital twins is being able to bring all of this data together, put it into a unified model, put it into a nice grounded picture, and then use lots of different technologies to facilitate lots of different decisions. So there's my 2 pence on this. I'm going to chuck it back to you, Mays, to talk about where this is all going.
Thank you very much, Toby. That's indeed. Now, think about the number of stakeholders in one organization. And now I'd like you to think about what digital transformation is doing to organizations. So I'm sure I hope at least few of our audience have heard of the term digital transformation. If you did so, do raise a hand or write something in the chat so we know. Basically, what that means is that an organization will not only digitalize their data, meaning they move away from paper towards digitally stored and managed data, but they are also making their operations digital. So they are also making their processes internally within the organization digital. And a lot of them, and if you do the two together, you are into digital transformation. And now, if you think about a bank doing that, and if you think about a farm doing that, and a fabric factory is doing that, car manufacturer is doing that, pretty much it's seeping through the different sectors and operational organizations within the society. All of them are integrating IoT devices, so sensors. So cars are now an ecosystem of sensors and controllers. What you end up with is a continuum whereby large amounts of physical infrastructure that are structured and correlated, feeding you large amounts of data and increasing actually amounts of data. These amounts of data need to be correlated, need to be analyzed. So that's where AI and coming into place. AI, you don't have one model. You don't take LLM and use it for everything. You don't take traditional machine learning models and use them for everything. So you need to choose the right model. You train it with the right data. Ultimately, as we move 10 years away from now, you might end up with models pre-trained on data of long lineage. So now the model itself becomes the data. You take these models together with the data you're getting them, and you draw intelligence, and then you retrain the models, and you draw recommendations on how do you change operations in your system, how do you reflect, how do you achieve different decisions by different stakeholders, the ones that Toby has just mentioned. So the recommendations could be coming to the technical manager in such a frequency. They could be coming to the executive manager at a different frequency. The two decisions might impact the system in different ways, correlated ways, resulting in new data, new models being trained, and you have a continuum of data flow into AI, influencing decisions, ultimately with the objective that you end up with a future system that is optimized to the best possible within its operational constraints. It is sustainable in the long term. Another important aspect that will come in from digital twins into future system is in the next slide, which is the proactivity. If you think about existing systems, they are largely reactive, and we're not saying reactive is going to disappear. No, you would still have systems that if something happens, they will react to it. But the important element coming in the future is proactivity. If I go back to the car analogy, few previous cars, past cars, you drive in, if you need to change gear, if you continue driving on the same gear, the car eventually will start making weird noise that tells you that you need to change gear. In modern day cars, if you drive and you are on the wrong gear, if you are driving manual, I know that a lot has moved to automatic. If it's automatic, it will proactively change as it detects your speed. And the same will happen in future systems. You will have real-time predictions that are so accurate that it allows you to have proactive communications. And because this intelligence is coming in a unified way, the communications and the proactive predictions are more and more reliable, are more and more trusted. And the recommendations that they are making have more and more trust into if I implement them, they are going to result into the predictive outcome that the model is telling me. Also, having digital twins allows us to suppress a lot of the noise data that comes from systems. I'm talking about the car analogy. If you look actually at any system and the amount of data it generates, a large volume of that is simply noise. It allows more digital twins will allows us to filter that noise out so that we can have explainable outcomes of our analytics. And when we test different what if scenarios, it allows us to see clearer what will be the outcome of this scenario. And then it will allows us to generate cohesively correlated decisions for those different stakeholders in an organization. So ultimately, it ends up with an evolved context with the lesson that the different stakeholders can learn from, which then can result in new recommendations of actions that ultimately lead to new predictions, and the cycle continues. I can see some questions in the chat. So, Toby, I don't know if you would like us to make a pause to comment on them, or is that at the end? You are muted, Toby.
Oh,
You-
no, let's go back to that. Here we go. Sorry, I'm having trouble driving. Yes, no, let's cover some of the questions now because it feels like a natural sort of stop point. Just building on what you've just said, Mays, I think that I do think that right now systems are generally passive. A lot of what we're speaking about is passive, so it requires a human being to go and search for the intelligence or pull the intelligence. I think the world that I can see, especially with the improvements in intelligence, the connection of AI and the physical world through digital twinning potentially moves us into a place where the systems become much more proactive and effectively active participants in the operational landscapes. But yes, let's have a look at some of these questions. So we've got the top question here that just quite simply asks, what is the difference between a digital twin and a dashboard or simulation model?
do you want me to take that?
Please.
Okay. What's the difference indeed? A dashboard is basically a visualization. A dashboard. So the slides that Toby has at the moment is a form of dashboard. It's not interactive, it's static because it's just picture. Um, but that's what it is basically. It's an interface for me or you, the human, to interact with the system. Um, it's visual. That's why we call, I mean, it allows you. It's like the dashboard of a car. A digital twin is much more about that. Think of it this way: a dashboard is the tip of the iceberg, and the actual iceberg is 90% underneath. Behind the dashboard, which we use to interact with, there is a whole suite of backend services which actually does the analytics of the data. It pulls the data, curate the data, analyze it, correlate it, correlate intelligence, have it in a curated, visual friendly manner, then expose it to the dashboard. That's the difference between a dashboard and a digital twin, which is it might be relatively easier to separate. The one that gets tricky is a simulator and a digital twin. Now, simulator and a digital twin are semantically very similar to each other. A digital twin is essentially a simulator, and a simulator is a digital twin. The difference is in capabilities, and the two terms have evolved historically. In the past, we used to call these non-real representations of a system a simulator.
Mm-hmm.
Why do I emphasize non-real is because they were very simple. Well, they were much simpler. They were considerably and significantly simpler. Think about a network. For example, if I want to take my Wi-Fi network, we used to be able to simulate it with some software. This was based largely on assumptions and mathematical models without actual real data from Wi-Fi networks.
Yeah.
That was useful, but it missed a lot of the behavior that comes from a Wi-Fi network. Now, if you take data from Wi-Fi network now and you analyze it and you integrate what happens into your Wi-Fi router, what happens into your connection that goes into the wall, what happens if the number of users connected to the Wi-Fi change, and if you draw power data from the Wi-Fi, and you plug all of these into one system and analyze the actual real data from your Wi-Fi network, you end up with the digital twin. So a digital twin is essentially a much bigger simulator that takes into account real data, real system conditions in order to draw predictive analytics, which allows you to simulate what would happen to the system if you change configurations. A simulator doesn't have that amount of real data, unfortunately, back then. It was heavily reliant on mathematical models. And don't get me wrong, I'm not saying mathematical models are bad. They are the essence. But what used to happen in the past is we lacked these realistic insights that allows us to make realistic predictions. And this is what digital twins are doing at the moment. I hope that answered the question.
I think that's good. I think simulation is possibly the wrong way to phrase it. I think digital twins simulate, of course they do, but your distinction there between real data and synthetic data, effectively, but synthetic data created the numerical way. So numerical models, physical models, numerical models, backed by physical models. I suppose that's kind of where my mind immediately goes when we talk about pure simulation models. Real time data going into one of those would move it more towards a digital twin. We'll come back to questions. We'll make a little bit of progress. So I'm just going to sort of move now into building on that vision, I suppose, and talking a little bit about how Entopy sees all of this evolving and what we're working towards. So we see the opportunity to start building on digital twin and combining it very aggressively with artificial intelligence to create a kind of very active and proactive command and control or mission control kind of capability that has the ability to sit there, watch the situation, understand how the situation is evolving, and act effectively as a command and control layer. So deliberately provocative in terms of how we're phrasing this, but hopefully takes you into a slightly different space. So we have the continuously updating operational picture. That's another way of phrasing digital twin. And then we have proactive communication with operators and the ability to run scenarios and test what ifs. So if I talk you through now a demonstration of what this looks like, that hopefully brings everything that we've spoken about to a sort of head, and we'll be in a position hopefully where we're either at time or we can finish off with a few questions. So let's start with the continuously updating operational picture. So the way that Entopy's technology does this is we take data from lots of different systems and we feed that into an ontology along with predictive models, so artificial intelligence models. And this is the area that us and Mays and the University of Essex are collaborating on to actually make sure that we can deploy micro models where data availability is perhaps a challenge. But we have 1 to 5 there, so we get the data from multiple sources feeding in, giving us the real-time sensory understanding of what's happening in the physical world. And AI models, so this is a data-driven approach to predicting what's going to happen in the future. So you have past, present, and future state being orchestrated effectively by an ontology. This creates a unique, effectively world model or digital twin for that particular organization that's maintaining a live spatial and temporal understanding of state. Like I said, ontology is the absolute center point to that. It's one of those technologies within the periodic table that I shared earlier. The result is a unified intelligence layer that can support different stakeholders across the organization. So we have lots of different services. You have a dashboard, of course, but then you have some AI agents that can start to interact with that unified intelligence layer to bring it forward. So the demonstration that I'm going to show you is a deployment that we have with Harwich Haven Authority. So if I just go to the next screen, this is the objective. So this is an ecosystem. And this starts to ground everything we've spoken about in a real use case. So we've spoken about cars. I'm now going to speak about vessels. So these are enormous container vessels that are coming into the port of Felixstowe. The fragility across this ecosystem is that there's lots of different stakeholders working together to facilitate the movement of vessels inbound and outbound to, like I said, the port of Felixstowe, but other ports as well. There's 5 ports, I think, in total in Harwich Haven's jurisdiction. And lots of stakeholders have to work together to manage their respective resources to support vessels coming into and out of. So the systemic fragility is the shared resource allocation across the operation. So we need a digital twin or an intelligence layer supported by a digital twin to proactively identify resource constraints, to understand how time, schedule changes, weather changes may affect the operation. We need to understand and model cascading impacts. So that's live simulation, if you like. And we need to be able to monitor and understand dynamic communications and comms. So let's say, for example, there is a reschedule last minute. What does it do? Where does that affect? How does that affect the operation? What do I now need to do to support that? Or if I want to say, if I make this schedule change next week, what happens? And being able to interact with a digital twin that's got the full picture, it's got all of this data semantically organized and orchestrated, it's built on a simulation, and it can run all of this sort of stuff is really, really available. So what does it look like? These digital twins don't necessarily have to be 3D models. Sometimes they are. In this particular case, it's a traffic light system on a dashboard. And effectively what we're doing is we're looking at lots of different vessels coming into and out of the Port of Felixstowe. We're flagging where we think there may be a challenge or a challenge emerging. Now, we have a concept called connected digital twins at play here, because first we've built a digital twin of the environment. So what we want to do is map and model the environment. So we're using things like geofences and spatial analytics to sort of understand where things are. And this is effectively the rule book, the textbook of the operation. This is how it works. These are the various different parts of that environment. These are the bits that are important. These are the rules that are associated with that particular segment of the channel, for example. We then have machine learning models that are predicting what the weather looks like. But in particular, they're looking at the likelihood that pilot stations are going to be closed for boarding. And that affects the operation materially. So we have a really nice, excuse me, holistic digital twin that's pulling all of this information together. Interacting with that environment, we have vessels. And each vessel is put together as a vessel journey within the context of what we're doing. So within each vessel journey, we have lots of predictions, lots of these micro models that are predicting certain things, and then we capture the actual event, the observed outcome, and we compare to see how accurate those predictions were. Now, the concept of micro modeling is you deploy models to discrete parts of the operation. So the one I'm highlighting is how long is the pilotage movement duration going to take? And then we use ontology and the concept of digital twin to link all of these together to create a bigger picture. With micro models, we can then start to chain them together. So the outputs of one model become the inputs of the next. And that allows us to start predicting more material things, such as what time is the vessel going to be in this particular segment of the channel, which is really important operationally, both from a live operational understanding, but also a simulation and let's understand what's happening. Visualizations within this particular model are relatively straightforward. They're relatively lightweight. There's no 3D sort of BIM kind of system that we're interacting with. And of course, we can go in and have a look at each one of the micro models that we have integrated to understand and monitor accuracy. If I move on to the next slide, now what we want to do is, as Mays was talking about in terms of future state, we want to take the access to the intelligence from being passive, where a human operator has to go and interact with the dashboard like you just saw, to being active or proactive, right? So this is where the agent's watching that dashboard, and when it decides something needs to be communicated, it communicates. So we have an agent that's watching everything that's going on. It can form situations, track situations through their life cycle, understanding how they evolve over time. And when it feels the need to communicate something, it sends an email to an operator so that they can sort of jump in and do something about it. So this is the situation lifecycle dash within the Entopy system. We're currently tracking five situations. And what it's doing here is it's just sort of capturing lots of information from that digital twin. And it's identified that we have a particular issue. So there's an inbound that's now inside the live arrival window. And you can see how that situation has evolved, starting on the 21st and gradually moving through. So we can actually see how the system has continued to watch that situation. Every time it's evolved, it's sort of captured a note. It's building a really strong narrative of what's happened with this particular situation. And each one of these notices is linked to it sending a communication. So it's sending emails or Teams messages to people. If we watch something that's actually resolved, we can again see the life cycle that it went through. So it started off forming, it's escalated, it's become critical, it's communicated quite a few times, and then it's resolved ultimately at the end. And what it can then do is start to summarize all of that and gain learnings from that situation. So this becomes a memory effectively. So this is an AI using the digital twin to garner data, situational understanding, temporal understanding, and narrate over the top of that situation what's happening, when it happens, and how it's happened. And this is helping the system to build experience. And when it feels the need, it sends a message out to people. So in this particular case, it's saying, this particular issue is happening, and it makes a recommendation. And the recommendation is to do X, Y, and Z. And the key thing that I want to draw your attention to here is that it has given the reasoning behind the recommendation that it's sent as it being consistent with other situations like this that it's seen before. So this is kind of building that experience through the concept of language models integrating with digital twins. And then finally, if we want to go in and start running scenarios, yes, there are different ways to achieve this. So there are, it's horses for courses. But in this particular situation, I want to close a berth 9 for a 6-hour dredging activity. When do I do it? And so the system can basically go through and pull that information back for us. It's absolutely fine. This is the sort of surface that a strategic decision maker would use. And to basically, this is a tactical decision. But we can also pull other information back. And maybe if I want to make a more strategic or transformational decision, such as climate, so I'm looking at carbon emissions. I now want it to use that unified intelligence to do some analysis and tell me what things can I do to have the biggest carbon impact. And it gives us five scenarios, which is absolutely fantastic. I also want to know what other ports are doing. So it goes off and has a look and says, right, this is what's going on elsewhere. And using other simulation techniques, we could potentially run these scenarios that it's suggested through those other techniques and see essentially validate the outputs from there. So I think that brings us quite nicely to the end. We have 5 minutes left. And I think we can address a couple of the other questions, Mays, before we close. So
Absolutely.
do you have any further comments before we go into Q&A, or shall I ask you? I'm actually going to ask you. I'm not going to give you the choice. At what point, the question is, at what point does a system become a true digital twin? Mays, if you could take that, that would be fantastic.
That's a good question. The devil is in a true. What is a true digital twin? I mean this goes into opinions potentially, but true is not a binary whereby you have a true digital twin and untrue digital twin. It's how realistic does it capture your system. Simulators were digital twins, but they were not necessarily to a large degree or to large extent capturing what systems do, at least not in certain situations and not in certain circumstances. So a true digital twin could potentially be a spectrum of realities. And the more that your digital twin can capture the reality of your system, the behavior of it, and the consequence on data that comes from different decision making, the more true it is. I would define it that way, but it's quite a spectrum. The more you can achieve it in a realistic fashion, the more true it is. But you have to take the truth of digital twins together with the cost and sustainability of digital twins as systems. And you want to find that sweet spot where you have reasonably truthful predictions coming from your digital twin at reasonable cost. I hope that answers the question. Toby, feel free to comment on it as well.
Yeah, I think that does. I think that covers it really well, Mays, to be honest. I think there's my personal view on this is that too much emphasis is spent on this debate. And actually it doesn't really matter. I think hopefully what we've got across throughout the last hour is that it's a really diverse topic, but it's a very, very important one because digital twin is the best way of describing everything that you've just seen. It's the most natural fit for description of what you've just seen, whether it's a numerical, numerical simulation or numerical model feeding into a simulation, or whether it's a data-driven approach. It really doesn't matter, providing the outcomes are achieved, and that's what's necessary. I think the thing that's really driving it is this connection of AI to the physical world, and I think that's a really, really important point. The actual true definition of at what point does a system become a true digital twin is the two-way interaction. And that is the true definition, or certainly the general consensus definition in the UK. Like I said, driven by the Digital Twin Hub and the really, really clever people there. The general consensus is that a true digital twin is something that takes data from the physical world, but then affects change in the physical world as well. So it's sort of a cyclical kind of two-way thing. And then when that change happens in the physical world, it updates the model. So it's a kind of continuously always on, very much data-driven kind of thing. And there's a spectrum that they use to define. So that would be the true thing. But my salient point is that it doesn't overly matter. Right, I'm going to bring things to a close now because we're 2 minutes from the top of the hour, and this is a lunch and learn, and we're going to respect everyone's time and say thank you all very, very much for joining us today and listening. I hope you found it useful. Mays, thank you very, very much for joining us today. I must say to the audience, Mays is one of the leading brains on this sort of stuff. So we've been very, very lucky to have you join. So thank you very much. The final point to make is that the next session, the next Lunch and Learn session is on the 19th of May. And in that session, we are going to be discussing different types of AI. So potentially a very interesting topic, a very hot topic. So yeah, I've just got the Q&As come up. There's just a question here. Will the recording be shared later? Yes, it will. Yes, that question will. We can say yes to that. So everyone that's registered to this event will receive an email with the link to the recording, so we can cover off then.
Thank you very much for having me, Toby, and thanks for everyone who joined us. This has been an absolute pleasure, and I must say also it's an absolute pleasure to collaborate with Entopy on real world use cases.
Bless you. Thank you. Thanks, everyone. Have a lovely day, and hope to see everyone again soon.
Thank you. Bye bye.